Now let us see the procedure how to convert a quadratic form into canonical form. Okay, so a quadratic form is given for you and you need to convert it into canonical form. Let us see the procedure. The first step is, let us find matrix of quadratic form. Find matrix of quadratic form for given quadratic form. Okay, a quadratic form is given. The first step is, let us identify the matrix of quadratic form. Okay, then second step is find the eigenvalues and eigenvectors. Find the eigenvalues and eigenvectors of A, where A is the matrix of quadratic form. Okay, matrix of quadratic form is taken as A. Let us find the eigenvalues and eigenvectors of A. And important point is, let us see all the eigenvectors are mutually orthogonal or not. Let us see all the eigenvectors are mutually orthogonal or not. Okay, if they are not mutually orthogonal, let us take help of a new vector ABC and make the vectors as mutually orthogonal. Suppose the eigenvectors are not mutually orthogonal, then let us take a new vector ABC and make the vectors as mutually orthogonal. Okay, so now let us assume that all the eigenvectors are mutually orthogonal. Okay, now let us form a new matrix called model matrix given by x1, x2, x3. Okay, where x1 is column matrix, okay, and it is eigenvector of one eigenvalue. x2 is also column matrix, it is also eigenvector of other eigenvalue, and x3 is also eigenvector of the third eigenvalue. The important point is all the three eigenvectors must be mutually orthogonal. Okay, if not, make them mutually orthogonal with the help of a new vector ABC. Okay, now let us form normalized model matrix. It is denoted by P cap. Normalized model matrix is obtained by dividing each element in the column with its length. By dividing each element in the column with its length, you will obtain normalized model matrix. Then okay, so every quadratic form can be represented in the matrix notation of order 1 by 1. Okay, so this is the important point. Every quadratic form can be represented in matrix notation of order 1 by 1. That is, for example, if x square plus y square plus 2xy is the quadratic form, then it can be assumed as 1 by 1 square matrix. Okay, x square plus y square plus 2xy is the quadratic form. So we have assumed it as, since there is only one element, you can assume it as 1 by 1 square matrix. Okay, so the 1 by 1 square matrix is same as x transpose Ax. Okay, if a quadratic form is given, it can be assumed as 1 by 1 square matrix that can be further represented as X transpose AX, where X is column matrix having the variables. Okay, there can be any number of variables. Okay, it can be of 2 variables or it can be of 3 variables. In our syllabus we talk about 2 variable and 3 variable quadratic form. Okay, and A is matrix of quadratic form. A is matrix of quadratic form. Okay, so a quadratic form is given. We have assumed it as 1 by 1 square matrix, and it can be further written as X transpose AX, where capital X is the column matrix containing the variables such as XY or XYZ, and A is the matrix of quadratic form. Now let us take a substitution. Substitution X equals to P cap Y. Now let us make a substitution. X equals to P cap Y, okay, where X is the column matrix, either XY or XYZ, and P cap is normalized model matrix, and Y is again column matrix, Y1 Y2 or Y1 Y2 Y3 as per the requirement. Okay, after substitution it will be P cap Y transpose A P cap Y. Okay, so after simplification you will get Y transpose P cap transpose A P cap Y into Y. Okay, normal matrix simplification, it will be Y transpose P cap transpose A P cap whole into Y. Okay, on simplification you will get the required canonical form. It will be some lambda 1 y1 square plus lambda 2 y2 square plus lambda 3 y3 square. On simplification you will get some lambda 1 y1 square, some lambda 2 y2 square plus some lambda 3 y3 square. So this is the required canonical form for the given quadratic form. If we assumed as the quadratic form is in 3 variables x, y, z. Okay, now let us see the procedure once again. A quadratic form is given. Quadratic form means it is a second degree expression. It can be in 2 variables or 3 variables. Okay, it has both product terms and square terms. Okay, quadratic form means it is of degree 2. It has both square terms and product terms. You need to convert into canonical form. Canonical form is also of degree 2. It has only square terms. Okay, now let us consider the given quadratic form and find the matrix of quadratic form as discussed in the previous class. Okay, so in matrix of quadratic form you replace principal diagonal with the coefficient of square matrix and non-diagonal elements with half of the coefficient of product terms. Okay, that is matrix of quadratic form. Let us denote matrix of quadratic form by A. Then find the eigenvalues and eigenvectors of matrix of quadratic form. Check whether all the eigenvectors are mutually orthogonal or not. If not, make them mutually orthogonal with the help of an additional vector a, b, c. Okay, assume all the vectors are mutually orthogonal. The vectors are x1, x2, x3. Then form model matrix. Model matrix is a 3 by 3 matrix. Okay, first column will be first eigenvector, second eigenvector, third eigenvector. Okay, now let us form a new matrix, normalized model matrix P cap, where each element has to be divided with its length. Okay, the difference between P cap and P, in P cap each element is obtained as divide each element of P with its length. Okay, it will be P cap. Now consider the quadratic form. Quadratic form can be assumed as 1 by 1 square matrix. It can be given the matrix notation as X transpose AX, okay, where X is the column matrix, XY or XYZ, and A is the matrix of quadratic form. Now take the substitution capital X equals to P cap Y, and on simplification you will get some lambda 1 y1 square plus lambda 2 y2 square plus lambda 3 y3 square. This is the required canonical form for the given quadratic form. And one more point, lambda 1, lambda 2, lambda 3 will be definitely the eigenvalues of the quadratic form A. And it is the important point. Lambda 1, lambda 2, lambda 3 will be definitely the eigenvalues of the matrix of quadratic form. For reducing a quadratic form into canonical form, and the name for this procedure is orthogonal reduction. So we are doing the conversion with the help of orthogonal reduction. In addition, the nature of quadratic form is also asked. Okay, let us see what do you mean by nature of quadratic form. Okay, first one, positive definite. A quadratic form is said to be positive definite if all the eigenvalues of matrix of quadratic form are positive. Okay, quadratic form is said to be positive definite if all the eigenvalues of matrix of quadratic form are positive. Okay, and it is said to be negative definite if all the eigenvalues of matrix of quadratic form are negative. Quadratic form is said to be indefinite if at least definite if some eigenvalues are positive and some eigenvalues are negative. Okay, and quadratic form is said to be positive semi-definite if at least one eigenvalue is 0, remaining all are positive. And quadratic form is said to be negative semi-definite if one eigenvalue is 0 and remaining all negative. Remaining eigenvalues are negative. Okay, there are totally 5 definitions: positive definite, negative definite, then indefinite, then positive semi-definite, then negative semi-definite. Okay, so quadratic form is said to be positive definite if all the eigenvalues are positive. Okay, it is said to be negative definite if all the eigenvalues are negative. It is said to be indefinite if some eigenvalues are positive and some are negative. It is said to be positive semi-definite, one eigenvalue is 0 and remaining are positive. It is said to be negative semi-definite if one eigenvalue is 0 and remaining are negative. Okay, totally 5 definitions. Suppose in one case one eigenvalue is 0, one eigenvalue is positive and one eigenvalue is negative, then it comes under indefinite. Okay, so it is about positive, negative, indefinite, positive semi and negative semi. Okay, then rank of quadratic form. It is the other point in nature. So rank of quadratic form is number of non-zero terms in its canonical form. Okay, after finding the canonical form, the number of non-zero terms gives the rank of quadratic form. Okay, then index of quadratic form. Index of quadratic form, it is the number of positive terms in the corresponding canonical form. Okay, number of positive terms in the corresponding canonical form is called as index. It is the number of positive terms in its canonical form. After reducing the canonical form, the number of positive terms gives the index. And the next one, signature. Signature of quadratic form. Okay, so it is the difference of number of positive terms and number of negative terms in the corresponding canonical form. Okay, it is the difference of number of positive terms and number of negative terms in its canonical form. Okay, so signature is difference between number of positive terms and number of negative terms in the corresponding canonical form. And one more point, matrix of linear transformation. Okay, so it is denoted by x equals to p cap y. Okay, where x is column matrix either xy or xyz, and y is column matrix y1, y2, y3. Okay, and p cap is normalized model matrix. It will be obtained from model matrix. Dividing each element of model matrix with its length, we will get normalized model matrix. So x equals to p cap y represents matrix of linear transformation. This all comes under nature of quadratic form. Positive definite, negative definite, indefinite, positive semi-definite, negative semi-definite, rank of quadratic form, index of quadratic form, signature of quadratic form, and finally matrix of linear transformation. Okay, in the next class, let us see how to convert a quadratic form into canonical form in 2 variables as well as in 3 variables. Okay, the approach we applied here is called orthogonal reduction, and the important point is you need to check whether all the eigenvectors of matrix of quadratic form are mutually orthogonal or not. If they are not mutually orthogonal, you take the help of an additional vector ABC and see that all the eigenvectors are mutually orthogonal. Okay, today I am going to explain a problem how to convert a quadratic form into canonical form by using orthogonal reduction. Okay, the quadratic form is given as 2xy plus 2xz minus 2yz, and also you need to find rank, index, signature, matrix of linear transformation, and also you need to discuss the nature of quadratic form. Okay, so you need to apply the method orthogonal reduction. Okay, now let us start with the problem. So given quadratic form is 2xy plus 2xz minus 2yz. Okay, so a quadratic form is a second degree expression. It can have square terms and product terms. Since it is having product terms, so it can be considered as quadratic form. So you need to convert this into canonical form. A canonical form is again a second degree expression where it only have square terms but not the product terms. Okay, so let us write matrix of quadratic form from this expression. From this quadratic form, let us write matrix of quadratic form. Okay, this is equals to, okay, first you need to place coefficient of square terms in the diagonal. Okay, and also the order of this square matrix is 3 by 3. Since it is the quadratic form in xyz are 3 variables, so this is a matrix of order 3 by 3, square matrix of order 3 by 3. Okay, the square term coefficients are 0, 0, 0. You need to place those coefficients along the principal diagonal. Okay, place the coefficients of square terms along the principal diagonal. So in order to fill the non-diagonal elements, let us assume x as 1, y as 2 and z as 3. Okay, now you take xy term, the coefficient is 2, divide the coefficient by 2, it will be 1. Okay, now you place 1 in 1 2 position as well as 2 1 position. Okay, now take the next product term. The product term is 2xz. Okay, the coefficient is 2, divide the coefficient by 2, the new number is 1. So place 1 in 1 3 position as well as 3 1 position. 1 3 position as well as 3 1 position. Now the next term minus 2yz, the coefficient is minus 2, divide coefficient by 2, it will be minus 1. Now place minus 1 in 2 3 position and also in 3 2 position. Okay, place it in 2 3 position and also 3 2 position. Okay, so this is called matrix of quadratic form. Now let us find the eigenvalues and eigenvectors for this square matrix. For this square matrix, let us denote it by A. So now you need to find eigenvalues and eigenvectors for this square matrix. Okay, so in order to find the eigenvalues, let us consider the characteristic equation. Let us consider characteristic equation in order to find the eigenvalues. So characteristic equation formula is determinant of a minus lambda equals to 0. Here it will be determinant of A. A is matrix of quadratic form. It is 0, 1, 1, 1, 0, minus 1, 1, minus 1, 0, minus lambda into 1, 0, 0, 0, 1, 0, 0, 0, 1 is equals to 0. Okay, now subtract corresponding elements. It will be determinant of minus lambda 1, 1, 1 minus lambda minus 1, 1 minus 1 minus lambda is equals to 0. Now we need to expand this 3 by 3 determinant. Okay, so let us continue from this determinant. It will be minus lambda into you close row 1 and column 1. It will be minus lambda minus 1 minus 1 minus lambda, then minus 1 into, now you close row 1 and column 2, it will be 1 minus 1, 1 minus lambda, plus 1 into, now you close row 1 and column 3, it is 1 minus lambda, 1 minus 1 is equals to 0. Okay, now let us expand this. Minus lambda into lambda square minus 1, minus 1 into minus lambda plus 1, 1 into minus 1 plus lambda is equals to 0. Okay, now let us simplify this. It is minus lambda cube plus lambda minus 1 plus lambda equals to 0. It is minus lambda cube plus 3 lambda minus 2 is equals to 0. Okay, so this is the characteristic equation corresponding to matrix of quadratic form A. Now you need to find the roots for this characteristic equation. Okay, so there are two ways to find the characteristic equation. One way is using scientific calculator, the other way is by applying synthetic division method. Okay, let us apply synthetic division method in order to find the roots. Okay, identify a number so that this equation will be satisfied. Let us start with 1. If you substitute lambda equals to 1, it will be minus 1 plus 3 minus 2 equals to 0. So 0 equals to 0. So on substituting lambda equals to 1, this equation is satisfied. So 1 is a root by using remainder theorem, and you take synthetic division procedure. Okay, highest coefficient to lowest coefficient. If any term is missing, then write the coefficient as 0. So minus 1, lambda square is missing, 0, lambda coefficient constant. Now you write 0, add these two, it will be minus 1. Multiply these two, it will be minus 1, add these two, minus 1, multiply these two, minus 1, add these two, 2, multiply these two, it is 2, 0. Okay, now you can write it as lambda minus 1 into minus lambda square minus lambda plus 2 is equals to 0. The new coefficients are obtained from the synthetic division table. Now you need to factorize minus lambda square minus lambda plus 2. So it is lambda minus 1 into minus lambda square minus lambda plus 2. Okay, it is lambda minus 1 into, you need to write middle term as sum of two terms. Okay, so it will be minus lambda square plus 2 lambda plus lambda minus 2 lambda plus 2 is equals to 0. Then it will be lambda minus 1, take minus lambda common, lambda plus 2, take 1 common, lambda plus 2 is equals to 0. So the factors are lambda minus 1, minus lambda plus 1 and lambda plus 2 is equals to 0. Hence the roots are 1, minus 1 and 2. Okay, so these are the roots. These roots are called eigenvalues of the matrix of quadratic form A. Okay, it is not minus 1 plus 1, or the eigenvalues of A. Okay, now after finding eigenvalues, you need to find eigenvectors corresponding to these eigenvalues so that the eigenvectors are mutually orthogonal.